everyone. Thank you for coming to the first week of SPAAM for the term. Our first speaker for today is going to be Luke, and he's going to be talking about data-driven contact networks for epidemic simulation. So it's yours.
So I'm going to start off with a motivation for my work. So in epidemiological modeling, modelers often use compartmental ODE models. So one where people go from susceptible to infectious and then to recovered. And in these models, it's often assumed that people interact equally. So each person in the simulation interacts with everybody just a small bit. But that's not really accurate. In the world, we can't see everybody in the UK at the same time. And this kind of changes the secondary case distributions. So in reality, many diseases are reported as negative binomial secondary case distribution. So there's a longer tail where some people meet and interact and spread disease to many more people than the average. And so our modeling efforts try to incorporate this into our modeling. And so we use networks. So networks kind of naturally incorporate this secondary case distribution by people only interacting and only spreading diseases to their neighbors, people that they're connected to. And this allows for analysis at an individual level. Protocols to stop disease spread. So there's no standardized approach to build these networks. So we're trying to build a way to go from the most commonly collected type of data for these networks to a full network that can represent our population we use for outbreak simulation. So the data that we use is called ego networks, and they're surveys where people tell the survey how many individuals they interacted with over a certain time period, often a day. So we have an example here from Comics, which is a data set we use throughout, and this is over 2 time periods. So Comics is taken during COVID. So this is when school. This is a student. He's in school, and this is when schools are closed right after the first lockdown, and he only has 2 connections. There are 2 connections at home because they're both green, and they're his family members. And then that same student, a few weeks later, when the schools open back up, have all of these connections that are in school of their classmates and teachers, and so they become much more capable to spread disease at this time. There's also differences in individuals, not just through time, but each individual has very different contact patterns. So we can see here that there's a general manager who has hundreds of contacts in a day. So they meet 245 people here at work, 64 outside of work, and 3 of their family members. And she's a general manager. So that's part of her job, that she has to meet more people. And then we have someone like a mathematician who meets 1 other person in their family in 1 day during COVID. And we try and capture this in our modeling. So we've got these, they're like puzzle pieces. So they're like a snapshot of the population on a certain day. And with loads and loads of snapshots, we try and build a representative picture of our whole population. In a perfect world, we would try and just know our entire population and who they meet every day. This is infeasible because this is dynamic and it changes every day, and there's just too much data for us to collect. So these representative models that we make try and inform our modeling approaches. So often when people are collecting this data, they use it by looking at contact matrices that look like this. So in the bottom left here, we have the youngest people, and as you go across the X and Y axis, people get older. And so often people meet people the same age as them much more often, and people meet 1 generation above and below them more often than they would their grown-ups. So especially at home, this is very easy to see. So this is a contact matrix from Polymod during from contacts that are made at home. So you can see this band of same age contacts and 1 generation above and below. In work, it doesn't follow the same thing. You just kind of have a working age blob of people. And here we have some teachers that interact with young people while they're at work. However, inside each of these like dots, there's some distribution where some people meet a very low amount of people or most people meet a very low amount of that age group, but then some will many. So we have here someone who meets a few hundred within this. This is the 18 to 29-year-olds in comics, and we have this person down here who meets a few hundred people in a day, and then you've got most people who meet one or two. So when we're building these networks, we're trying to incorporate not just this contact matrix, this average mixing, we're also trying to get this distribution that underlies the mixing. So in a longer talk, I would tell you about how the inner workings of my model work, but I don't think we have time for that. So I'm just going to say we have some approach that incorporates both of these things, and it fits a distribution to the age group, and so it fits a distribution to this, but also at the same time, and then connects people based on these distributions. And when we're trying to look at how well we've done, the comparator is this stochastic block model, which would be the commonly used model for this type of modeling, where you incorporate age. So you've got, as you go up in age, you've got these school age people who meet more than the average, and then you've got that working age block we were talking about. And in this is the stochastic block model. It can't incorporate this heterogeneity in contact distribution that we saw earlier. So some people meeting much more than the average, because it pulls from a Poisson distribution. So you can see they're all kind of homogeneous in close to the average of each block. In the middle, we have the data, which looks quite different to that. And then my model, which maybe looks a bit more accurate, but it's kind of hard to tell from just an image like this. So we have to find a method to actually calculate how accurate our model is to the data. To do this, we use optimal transport. So optimal transport is a way of looking at the similarity between two distributions. So imagine that one of your distributions is a pile of dirt and the other one's a hole, and you want to see what's the difference in the mass between each and how much effort it takes you to pick up the pile of dirt and move it to the hole, and where effort is the weight of the dirt multiplied by the distance you have to travel with the dirt. And if we think of each person as a distribution like this, so we have a person from the model and a person from the data, we can use this optimal transport to look at the difference in their frequency distributions, and then calculate a cost of making one person into another person. Once we've done this, we do it for the stochastic plot model, which is the best that's out there at the moment. My model, don't worry about the orange one, look at the green one. The orange one is just my model with a negative binomial instead of a power law degree distribution. And we can kind of see that there's much less error when we can actually capture this heterogeneity in degree distribution. Because the blue line will perfectly capture these contact matrices, but it won't capture that some people meet many more than others. So once we have that, I was happy that my model is pretty accurate to the data, but the idea of the modeling is to do outbreak simulation. So this is an outbreak on my model. The blue line is these compartmental OBE simulations. And we can see that the disease doesn't really take off if we assume that every contact is equal. So the people who have thousands of contacts, interact with that contact just as much as someone who has 2 or 3 contacts. Then the disease, to capture a common early outbreak growth rate, the people with the large amount of connections drive it early, and then once these are used up, the disease kind of dies out. And that is because we're trying to fit to an early growth rate, which is what many modelers try to do. Whereas if we go to the stochastic block model, it makes something closer to what we'd expect, where we don't have anybody who's really connected, but everybody's quite connected, and it's much easier to spread disease. So with the same early growth rate, this is what an outbreak in the stochastic plot model looks like. Not to say the stochastic plot model is perfect. It doesn't capture the dynamics of the disease at an individual level, but it better captures the overall final size and infection curve. But we want to be able to capture this underlying network structure accurately, but also this final size and this ability to predict the outcome of disease. So for a COVID-like disease, we chose. We said that we need to actually think about the disease itself. So if we have like a COVID-like disease that passes through the air, the amount of time and the physicality and how close you are to the person that you're in contact with matters. And so far we hadn't really been modeling that. So we use there's information on the duration of each contact, there's information on the physicality of each contact and how often people see each other in this data as well. So if we try and use that along with our degree distributions, we can kind of dampen this effect of the super spreaders that are causing all of the outbreak in the power law model. So as you can see here, as the number of contacts increase, the amount of time you spend with each one on the y-axis decreases, and so you'd be less likely to spread disease to people that you only spend a few minutes with at a time. And so if we do that, we get, this is the final size by the early growth rate of our outbreak, and we can see here, this is the double Pareto without the scaling. So the outbreak just can't really take off, because if you force it to have such a small early growth rate, where the super spreaders are taking control, once it leaves them, the rate of spread drops drastically and the disease dies out quickly. We have the black line is compared to a low DE model. The stochastic plot model is quite close to it, so it has really large final size, quite close to the homogeneous model. And then when we scale by duration, it gets closer and it gets to a stage where we can actually use this to model outbreaks, whereas this one we wouldn't have been able to while trying to incorporate this secondary case heterogeneity. So as we know, if the final size decreases, it's kind of in the literature, it's kind of known that the final size decreases as you increase heterogeneity. So this is kind of an expected result, but we were hoping for something that was still a final size large enough that you could predict real disease outbreaks. So as well as this, if we look at the actual secondary case distributions, the red line is COVID here. So this is the dispersion of COVID is somewhere between here. We had a look at some systematic reviews, and they say it's between 0.1 and 0.7, the dispersion parameter. So it's got a long tail. Super spreaders are quite important in COVID. With the stochastic plot model, the dispersion parameter, the higher the dispersion parameter, the less important super spreaders are in our model or in modeling. So for the stochastic plot model, where we don't have people that have a really high degree, we just capture the average mixing. This K is above 1, so there wouldn't a respiratory type disease like COVID wouldn't have something above 1. It wouldn't be so high. But if we look at without our scaling, it's below 0.5, and that's the green line here. And we can see it can't really be captured by it. This line isn't even fit very well because the negative binomial can't fit to this heterogeneous data set. So that's not really accurate to a real world either, because most of these diseases are captured by negative binomial distribution. And then when we scale by the duration of a contact, we get a K of 0.4, which is within our error bounds for our model. Or for COVID, which is kind of what we wanted. It kind of accidentally came out of it from our modeling approach, and it worked quite well. So that's it for me. Thank you for listening.